Okay, I think we wait for a little bit so that some people can still come after the photo. Okay, maybe we can start. So it is my pleasure to welcome Joseph Cunningham, who will tell us something about Eigenpath traversal.
Okay, thank you everyone for coming. So I will tell you a little bit about Eigenpath traversal and in particular doing it with Poisson-distributed phase randomization. This is joint work with my supervisor, Jérémie Roland, and the paper, if you want more information, is in the proceedings. So I will define what I mean by Eigenpath traversal, then tell you a bit about phase randomization, which is something that existed in our doing something. Maybe it needs to be closer. Okay, is that better? No. Yeah. Yeah. Okay. This is easier. Okay, great. Thank you. So yeah, into it. So what's the basic setup? Suppose you have a path of Hamiltonian. So you have a parameter going from 0 to 1, and you have, for each value of that parameter, you have a Hamiltonian. And suppose you start in a state, you have a system that's in a state that is an eigenstate of the starting Hamiltonian. Then the question is, can we kind of track the corresponding eigenstate as the Hamiltonian changes along the path? So for all values of the parameter, can you modify the state that you started with such that you stay close to a eigenstate of the Hamiltonian at each point along the path? And there are a number of procedures that do this. The most famous, of course, being adiabatic quantum computing. That's the whole idea behind adiabatic quantum computing, and then you use that to build algorithms to solve problems, right? But there are another number of other procedures that do something very similar. So one way is with measurements. Instead of kind of relaxing down into the eigenstate by time evolution, you can relax into the eigenstate by projective measurement. That's another way of doing that. Or you can use phase randomization. And this is a procedure that has been developed before and is maybe less well known than the other two, but is very interesting. And we will be building on this phase randomization. So some kind of pros and cons of the existing methods. Adiabatic quantum computing obviously has been very successful. It's very nice, it's very intuitive, but actually implementing it can be difficult. So of course, there are machines that implement it. If you go to D-Wave and you buy their machine kind of implements that. The disadvantage is that they only implement it for specific time-dependent evolutions. So you can't pick any initial and final Hamiltonian that you want, and you can't do any kind of path in between, but you can do certain paths in between. On the other hand, if you want to do this kind of thing, so you want to do a kind of the analog of adiabatic quantum computing on a conventional quantum computer, you run into discretization errors. And these are typically not negligible. On the other hand, what's nice about adiabatic quantum computing is that you have these nice kind of continuous evolutions. And so you have discrete, you have like differential equations, and you can solve your differential equations. You can get an adiabatic theorem. And based on this adiabatic theorem, you get nice results that are typically relatively easy to analyze. And in fact, they're so kind of nice that often even in kind of discrete algorithms, the underlying intuition somehow comes from an adiabatic evolution. And so we want to be able to, the main idea then is to be able to preserve these nice features of adiabatic quantum computing while moving to kind of operationally a more discrete picture, such that you don't have these extra discretization errors. And so what's the idea here? The idea is to, given this path that kind of exists abstractly, you want to sample along the path, pick a number of Hamiltonians, and then for each Hamiltonian in turn, you kind of want to nudge the system into or close to the eigenstate, towards the eigenstate that you're interested in. And so the major new aspect of this work is that we pick the Hamiltonians according to a stochastic process. And because you pick the Hamiltonians according to a stochastic process, and if you marginalize then over your like stochastic choice, what you get is a nice continuous differential equation for which you can write down an adiabatic theorem and for which you can analyze in the way that you're familiar. So, the new element is this stochastic picking of the Hamiltonians, but then you actually need to do the kind of discrete nudging operation. And for this nudging operation, we've chosen to use phase randomization, which is an existing technique. And so the basic idea is this. So given you've picked one of those Hamiltonians, you want to nudge your system into the eigenstate or closer to the eigenstate, which here is given by the P. And the delta, the gap, is the distance between the target eigenvalue and the closest rest of the spectrum. So typically your omega 0 here would be the ground state, and then the gap would be the first excited state. But we're not making the assumption that we want to go to the ground state. We might want to go to a particular state of interest that's kind of in the middle of the spectrum somewhere. And everything works in kind of the same way. Then we assume that we can do time-independent evolution of this Hamiltonian. And so this is a relatively kind of mild assumption in the sense that you can do this on a conventional quantum computer, right? So this is kind of operationally, this shouldn't be too hard to do. And notice that we have a cost model where the cost of doing this operation is t. And so you may be wondering, okay, but you can't actually do that on a quantum computer because you can't perfectly perform this Hamiltonian simulation. And then people will talk about the cost model in terms of numbers of applications of block encoded Hamiltonians or something like that. And I won't tell you much about that, only that it works. So all of the complexities I'm going to show here are in terms of the time t, the time complexities, but you can translate them to query complexities to compare it with the rest of the literature. There are some details about how to do that in the paper, but I won't really talk much about that here. And so then finally we get to the nudging operation. All we're doing is we're doing some kind of randomized time evolution. And the nudging operation, what does it do? Well, it essentially kills the off-diagonal blocks. So your density matrix is kind of projected into, you have the eigenspace parts and the completely away from eigenspace parts of the off-diagonal coherences are killed. So that was the kind of the discrete procedure that you do. And so the extra ingredient here is the fact that it's done according to a Poisson process. So so we start with a Poisson process, which is essentially a number of clicks. You jump at certain points along your path, but randomly, right? So when you actually, in practice, want to run your algorithm, you pick a Poisson, you pick a realization of the Poisson process, and then at the point where it tells you, you do this operation. And so like, okay, formally, this is what the algorithm says. You pick your Poisson process, and at every point you do this phase randomization. Then what you can do is you can write down a stochastic differential equation. So whenever you have a jump in your Poisson process, you also have a change in the density matrix, of course, because you do something at jumps. You don't do anything in between jumps. And what happens is exactly this. You have this time evolution is the kind of new thing, and the old thing you subtract away. Marginalizing over the different realizations of the Poisson process give you this nice stochastic differential equation, which you can rewrite in the following form. Now, notice that this is somehow has similarities to the normal Schrödinger equation down here. And so in adiabatic quantum computing, essentially what you want to do is you want to take this T here to be very large. And so if you take it large enough, then you will track the eigenstate relatively well, hopefully. And the same here, you have the same, which is the lambda. Now, the lambda is the rate at which the Poisson process clicks. So the higher the rate, the more clicks you have, so the more nudging operations you do. And kind of morally, you have exactly an exact equivalence between the two cases. Like, just like you want larger T in the adiabatic case, but of course, the larger the T, the longer the time and the less efficient your algorithm is. Same here, the higher your rate, the more like operations you have to do, so the less efficient your algorithm is, but the better the fidelity is at the end. And so then you want to kind of like work out what's the optimal kind of trade-off between those two things. So the next point is to say, okay, given that we've done that, how long has this taken us? So we've taken a realization of the Poisson process, and so at a number of points we've done something, and doing this something takes an amount of time. And so you add all of those things up, or you take the integral to be more precise, and this gives you an expression for the amount of time you've spent on your algorithm. And now the final kind of element of all of the elements that I'm trying to bring together into a final algorithm is like an actual guarantee that doing this procedure will get you close enough to your target state. And this is, so you can think of this as an adiabatic theorem. This is the adiabatic theorem that tells you somehow that if you take a good enough rate function lambda, that the fidelity that you get, or the infidelity rather, is small enough here. And okay, so if you know something about adiabatic quantum computing, maybe you know that the gap is a very relevant parameter. And I haven't said anything about the gap here, but rather I've got this strange thing with derivatives of the eigenprojector in some way. And actually the link is relatively straightforward. You can just bound one by the other. And that's how you get these bounds in terms of the gap. This is exactly the same thing as for the adiabatic, the kind of standard adiabatic theorem. Okay, so I've laid out a number of different elements of the algorithm, but before putting them all together into one big theorem and give you some like concrete results, I'm going to introduce two problems that we can use to kind of benchmark this proposal. The first is simple, Grover search. I'm sure everybody is well aware. So we have this projector on some subspace spanned by computational basis states, and we start in the uniform superposition. And so you kind of interpolate between a Hamiltonian where the ground state is this uniform superposition and a ground state where any element in, like any target element is a ground state. And then the other problem that I'm going to be talking about is the quantum linear systems problem, where essentially you want to solve a linear system of equations in a kind of quantum way. And so it's okay, there's a couple of things like you're not really finding a solution, you're creating a quantum state that encodes the solution, and it's of course normalized and all the rest of it. But that's basically the idea. And then I'm not going to tell you anything about the exact path that you need to follow to solve this, but suffice it to say that there is a path that has been analyzed in the literature. And essentially, we don't need to know very much about the path. All we need are a couple of spectral guarantees. And based on those spectral guarantees, we can fill them in the theorems, and we get a complexity. So what is the spectral information that we need? It's basically a bound on the gap. So, okay, side note, whenever I say gap in this talk, what I really mean is a bound on the gap. We don't need to know any like explicit calculations of exactly how big the gap is. As long as we have a bound, the better the bound, typically the better the algorithm. But so long as you know something about the gap, it will give you a correct algorithm. So, okay, you've got, these are gaps for kind of typical instances of both problems. Here, kappa is the condition number of the matrix A. So kind of typically the larger kappa, the kind of more difficult the problem is. The M and the N for Grover, M is the number of states that you can accept, N is the number of total states. And now there is one feature that is interesting, that this kind of, you can immediately see if you look at the two plots of the gaps there, is that you have this kind of straight line approximation. So like if you squint hard, and you'll see that essentially we're dealing with straight lines, and then you have a bit at the bottom that's small, and for the rest you have straight lines. And what's interesting about that is if you take integrals of powers of 1 over the gap, if you think of delta as just like being S, right? It's just something that's linear, then at the end you get 1 over the p to the minus 1. You reduce the order, right? You're just taking an integral of 1 over x to the p gives you 1 over x to the p minus 1. And so that holds for kind of the straight line segment, and it also holds for the gap, like the bits, sorry, the kind of bits of the middle, the bits close to the minimal gap, because they are relatively short. And so like putting all of that together, you get this basic feature. And this feature is going to be very important to show that the algorithms are optimal. Okay, so Grover is relatively simple. I'm assuming everybody kind of knows what it is. Quantum linear systems is a more complicated problem, and there is a bit of a longer history in trying to solve it optimally. So there's the HHL algorithm, which is kind of the first attempt at solving it. And then you have various other improvements that have kind of been, so various other improvements over the years with the optimal kind of optimal scaling in kappa given with a method originally given using the discrete adiabatic theorem, which is a kind of another thing that looks adiabatic, right? And then also here, the previous attempt before that used the randomization method, but not this stochastic randomization method. And so what they got was they got in kappa, but they had an extra log kappa factor. And so basically, part of our contribution here is to say, well, if you do this stochastic process, you have kind of a more continuous dial that you can tune. And with this more continuous dial, you can kind of nudge your rate in such a way that you can kind of tune away the log kappa. Okay, so this is a first big theorem. Here now we're assuming that the rate is constant. So assume you pick a constant rate, and then, okay, just filling everything and putting all of the elements that I've talked about together, you'll see that the algorithm is correct if your rate is larger than this number. And then you have a time complexity of this. And so you can work out what the actual time complexity is for these particular problems. For Grover, you get something that's not quite optimal. And this is to be expected because we know that adiabatic Grover without an adaptive schedule is also not optimal. And in fact, this is slightly better than the adiabatic case because in the adiabatic case, you get n over m without the square root. And here, at least, you get the square root, but you also get a log factor. Something relatively similar happens for the quantum linear systems problem is you get kappa, and then but you also have the log kappa. But we can go a step further because we've taken a very simple rate function. We've taken it to be constant. Now, what happens if we make it adaptive? Well, we can take it, for example, of the following form. This is a suggestion that happens to work quite well. And so, okay, you do all of the analysis, and then you get a time complexity of the following form. And this results in, for Grover, the usual scaling that you would expect. And for the quantum linear systems problem, this also gives you the optimal scaling. And again, right, so this is a time complexity, but you can then do the extra exercises of doing optimal Hamiltonian simulation on a quantum computer, and you will get that this is also the query complexity on a quantum computer. Another factor is that you have So in this choice here, in the suggestion that we've made of a possible rate, there is a certain amount of freedom with the Qs here. It turns out that we have to take the Q strictly between 0 and 1. And if you take it at 0 and 1, then you get an extra log factor. And we believe that that's more or less what's happening in the previous randomization attempt. Essentially, what was happening is that the Q was more or less taken to be 1, which is why there was an extra log factor. Yeah. So a last point about scaling in the precision. So adiabatic methods kind of naturally have a scaling of 1 over the epsilon, but there are techniques to kind of circumvent this. And they can also be done in this setting. So assuming you just have a device that can do this Hamiltonian simulation, okay, we give a little bit of information on how you could, even with such a device that's not a full quantum computer, how you could do this eigenstate filtering. Right, okay, that was basically it. To conclude then, so the main advantage of this method somehow is that it gives you continuous quantities, which seem to be easier to analyze in certain situations. You can write down a generalized adiabatic theorem. We have given, so the optimal complexities that I've quoted essentially are of the form 1 over the minimal gap, which if you know something about adiabatic quantum computing, that's kind of better than you would generically assume. And that's because we've filled in an adaptive schedule. For the quantum linear systems, we obtain the optimal asymptotic scaling. And so then, okay, what's the next step? Well, one thing that I would be very interested in knowing more about is, okay, we've got other discrete methods that we could randomize in this way. So for in particular, the discrete adiabatic theorem, I'd be very interested to know whether you can analyze it in a different way using these differential equations. Maybe there are insight to be gained there. Also, of course, other applications would be very interesting because these two applications have been well studied. We know a lot about them, but maybe this, because the strength here is somehow that this automatically, given an eigenpath, this automatically gives you an algorithm. You don't need to know much else. You need some spectral guarantees, but that's it. Can we think of other applications? And we have some results that these things work relatively well for Ising Hamiltonians. And then finally, okay, the scaling has happened in terms of the gap, but sometimes the gap might not be the optimal measure with which to work. And so we're thinking, can we deal with a sort of effective gap, just like you could potentially do in some cases for the adiabatic theorem. So yeah, that was basically it. Thank you.
So we have time for 1 or 2 quick questions.
Hey, I was wondering if you could say a little bit more about actually realizing it in terms of oracle calls to the block encoding of the Hamiltonian, because that's something that tends to be a bit tricky when you're doing this continuous time versions of these.
So, like in principle, it's relatively easy, right? Because we have algorithms on a quantum computer, we have algorithms for optimal Hamiltonian simulation. So in principle, all you need to do is, you take your Poisson process, you fix at every point, you fix your random time, and then you fill that in the algorithm, and that uses the block encoding. And so you can do that, and we've done the exercise in the paper, and you see that the scalings are exactly the same. So the query complexity is the same as the time complexity.
Okay.
Like you have to do something slightly complicated with the Q factor that I mentioned. Like not all of the Qs work equally well. So there is a bit of a trade-off, but like basically everything typically works out well.
Okay.
Okay, so maybe let's postpone the remaining discussion for the later. And thanks again for the nice talk. Okay, so let's welcome Girish, and she will tell us about some quantum communication advantages with one clean qubit.
Yeah, thank you. So thanks for coming. I'll be telling you about quantum communication advantages using just one clean qubit. This is based on a joint work with Srinivasan Arunachalam and Noam Lifshitz. Let me start by giving you the motivation for this talk. The motivating question is the following. Do quantum algorithms exponentially outperform classical ones? Well, given that this is a TQC audience, most of us believe that the answer is yes. But proving this belief is a very hard problem and would imply major complexity theoretic breakthroughs. So one can ask, are there settings where we can unconditionally prove this? It turns out that query and communication complexity are two striking examples of such settings where you can prove that quantum algorithms exponentially outperform classical ones. In this talk, the focus will be on communication complexity. The second question motivating our work is the one clean qubit model. How powerful are quantum algorithms with just one clean qubit? I will formally define these algorithms later, but roughly speaking, one qubit is in a pure state and all others are maximally mixed. And the question is, what kind of useful quantum computations can you do with such highly mixed states? Again, people believe that this model, despite being highly noisy, can exponentially outperform classical computation. But as before, we don't have a proof of this. So this leads us to ask, are there settings where we can unconditionally prove this? And this is the main result of our work. We prove that in communication complexity, the one clean qubit model exponentially outperforms classical communication. So this gives the first provable exponential speedup between the one clean qubit model and the classical model. In the rest of the talk, I'm going to define these models more formally and tell you more about the details, but this is the main takeaway from this talk. So let me start by introducing communication complexity. The communication complexity setting is a very important setting in complexity theory. This studies the amount of communication required to compute functions with distributed inputs. You have a function whose inputs are distributed between two or more parties, and their goal is to determine the value of this function while using as little communication as possible. This setting has several applications to lower bounds in streaming algorithms, distributed algorithms, and even classical circuit complexity. This has also played a central role in the field of quantum computation and information. There are many examples of quantum protocols that demonstrate the advantages of quantum communication or non-locality or entanglement and so on. There's also a long and rich history of unconditional exponential speedups of quantum over classical. We have many examples of functions for which quantum communication can provide exponential savings over classical communication. I'll tell you a little bit about the history of these results, but first let me formally define the communication complexity model. So here you have a function that depends on two n-bit inputs, x and y. Alice gets x, Bob gets y, and they want to determine f of xy. This function f might be a partial function. That is, it takes values in 0, 1, and star, where think of star as don't know or don't care. And the players are promised that they're given inputs x and y, such that f is either 0 or 1 on this input. And their goal is to determine whether it is 0 or 1. Now, since each player doesn't know the other player's input, they need to communicate in order to be able to evaluate this function. And their goal is to minimize the amount of communication. For example, Alice could simply reveal her entire input to Bob. In other words, she can send the description of x, which takes n bits of communication. And the goal is to do much better, to somehow be able to compute f by using only polylog n communication. We formalize this by the notion of a communication cost of a protocol, which is basically the maximum number of bits or qubits of communication that the players ever send. This is the broad setting of communication complexity. In a classical communication protocol, communication typically proceeds in rounds. And in each round, the player sends a message to the other player, which is a bit string. And finally, Bob announces the answer. We will always allow randomized communication. That is, the players always have access to shared randomness, and their messages can depend on this randomized string. And their goal is to compute the function with high probability, at least 2/3. This is the setting of classical communication complexity. And now we can talk about quantum communication complexity. There are typically two types of resources in quantum communication complexity. The first is the ability to send quantum messages. The second is the ability to share entanglement, typically between Alice and Bob, usually in the form of a few EPR pairs. These resources often behave incomparably, and there are many open problems regarding the interplay of these two resources. This is the broad setting of quantum and classical communication complexity. I'll talk about a few restrictive models of communication based on the number of rounds. So we can impose restrictions on the number of rounds of the protocol, that is the number of times that Alice and Bob can take turns when communicating. In the most restrictive setting, you have simultaneous communication, where Alice and Bob don't talk with each other. Instead, they send a message to a third party, Charlie. Charlie doesn't see the inputs of Alice and Bob. She only sees the messages, and based on the messages, she has to come up with the answer. This is very similar to the setting of non-local games. A less restrictive model is the one-way model, where Alice sends Bob a single message, and Bob must return the answer. The least restrictive model is the two-way model, where Alice and Bob can send messages back and forth, and finally Bob announces the answer. These are three successively stronger models of quantum communication, and you can come up with functions that you can solve with k rounds, but with k-1 rounds, the communication cost blows up exponentially. So now let me introduce the main problem in quantum versus classical communication, which is what is the power of quantum communication versus classical communication? Are there partial functions which can be computed using quantum protocols of small cost, but not any classical protocol of small cost? And as I mentioned before to you, the answer to this question is indeed there are many examples of functions that demonstrate such an exponential quantum speedup. And there is a long line of works showing many such examples. And loosely speaking, these works are trying to actually answer the more fine-grained version of the question, which is the following. What is the minimum quantum resource sufficient for an exponential quantum communication speedup? In particular, Gavinsky, who has thought a lot about these problems, asks, what is the weakest quantum communication model that outperforms its classical counterpart? What is the strongest classical model over which the quantum counterpart shows an exponential advantage? There's been a long line of works that are broadly motivated by trying to understand this question. And these are some of the most important results along these lines. The strongest of these results is the last one. Yeah. So the strongest of these results is due to Gavinsky and myself, Ran and Avishai. We show that quantum simultaneous communication, where Alice and Bob share entanglement, can exponentially outperform randomized classical two-way communication. So this is saying that a rather weak model of quantum communication can exponentially outperform a rather strong model of classical communication. And this result qualitatively subsumes these previous results. This is pretty much the state-of-the-art result, although recently there have been many works that try to remove the entanglement in this protocol, although they're only for relational problems and not for partial functions. So there is still a lot to be understood here, and improving this result is a big open problem. In our work, we morally try to improve this result by studying advantages of even weaker quantum protocols than these kind of protocols. Namely, we study advantages using one clean qubit protocols and entangled fingerprinting protocols. I will formally define these protocols in the next few slides. So first, let's start with the one clean qubit protocol. This is motivated by the one clean qubit model of quantum computing. This was defined by Cunningham and Laflamme, who are trying to understand the NMR approach to quantum computing, where mixed states are highly prevalent. So in this one clean qubit model, also called DQC1, there is one qubit that is in a pure state, and all others are maximally mixed. You're allowed to apply quantum operations on these states. And the question is, how powerful is this model? Interestingly, this model, despite being highly noisy, can solve some problems that are believed to be exponentially harder for classical algorithms. In particular, we know that under complexity theoretic assumptions, this model is not efficiently classically simulable. These results suggest that the one clean qubit model is indeed much more powerful than the classical model. And we ask, are there unconditional speedups? Are there settings where you can prove exponential separations between the one clean qubit model and the classical model? A natural setting to study unconditional speedups is communication complexity. So this brings us to one clean qubit communication. This was formally defined by Hartmut Clock and Debbie Lim. In this model, initially you have a state where the first qubit is in the pure state 0, and all other qubits are maximally mixed. That is there in the state identity over 2 to the m. And now Alice and Bob take turns applying unitary matrices on these qubits. We're going to assume that Alice and Bob don't have any other private quantum memory. All their memory is constrained to these qubits, and the only thing they can do is apply unitary operators and send them back and forth. The cost of the protocol is defined to be the number of rounds times the number of qubits per round. So in this example, it is 4 rounds of quantum communication consisting of m plus 1 qubits each. So it's 4 times m plus 1. This is the one clean qubit model of communication complexity. And Hartmut, Clock, and Debbie Lim ask, what is the power of one clean qubit communication? All the interesting examples of quantum protocols that we saw earlier in communication complexity seem to require at least log n qubits. And one can ask, what is the power of quantum communication when you have just one clean qubit? Can it, for example, be classically simulated? This is the main problem that we resolve in our work. We show that the one clean qubit model of communication is not efficiently classically simulated. In particular, we give an example of a partial function where Alice and Bob get n² bit inputs, such that this problem has a quantum communication protocol of small cost with just one clean qubit, but every classical randomized protocol is of exponentially larger cost. This resolves the conjecture of a Clock and Lim, and it gives the first unconditional separation between TQC1 and BPP in the communication. So this is our main result. I'd like to emphasize that the classical lower bound here holds for all classical communication protocols of small cost. So Alice and Bob can interact, and they have any number of clean qubits. So the lower bound is for a very strong model of classical communication, whereas the upper bound is for a very weak model of quantum communication, namely the one clean qubit model. So this is our main result. Let me also tell you the problem for which our main result applies. And our problem is called the ABCD problem. Here, Alice and Bob get unitary matrices. So Alice gets A, C, and Bob gets B, D, where all of these are n by n special unitary matrices. And their goal is to roughly tell whether the product ABCD is close to identity or far from identity. More precisely, they want to tell if the trace of A times B times C times D is large or small, where large is at least 0.9 n or at most 0.1 n. This problem is motivated by the trace estimation of unitaries, which is in some sense complete for DQC1. And this is a communication version of this problem. And we show that this problem has a one clean qubit protocol of small cost, but no small cost randomized classical protocol. So this is our first main result. Next, I'd like to talk about entangled fingerprinting protocols. Let me start by telling you about fingerprinting communication first. This was a model of communication defined by Boorman, Cleve, Waters, and DeWolf. This model consists of quantum simultaneous protocols where Charlie simply performs a swap test. So Alice and Bob get inputs X and Y. They send quantum states to the referee rho X and sigma Y. And the referee Charlie simply does a swap test between the two quantum states. This is a very restrictive type of quantum simultaneous protocol and is called a fingerprinting protocol. This model has some advantages over classical fingerprinting protocols. But once Alice and Bob have public randomness, this model becomes classically simulable. So in the presence of public randomness, this model has no quantum advantages over classical. You can mimic quantum fingerprints using classical fingerprints in the presence of randomness. What we study is entangled fingerprinting communication, which is essentially the same model, but Alice and Bob are allowed to start off with some entanglement. We will assume that the entanglement consists of a few EPR pairs. Alice can apply some quantum operations on her part of the EPR pairs. Bob can apply some quantum operation, and they can send all their qubits to the referee. And as before, Charlie just does a swap test. This is the entangled fingerprinting protocol. And what we show is, interestingly, this kind of protocols can show exponential quantum speedups. In particular, if you look at the ABCD problem that I mentioned before, this problem has an entangled fingerprinting protocol of small cost, provided Alice and Bob share a few EPR pairs. So this is saying that with just the resource of entanglement, fingerprinting protocols can exponentially outperform classical interactive protocols. So this is our second result. In the next 5 minutes or so, I'd like to tell you a little bit about the proof ideas. And this might be a little technical, but for those of you who are familiar with these analytical tools, I hope it will give you some idea. Right, sorry. So first I'd like to, let me mention this result in the context of previous work. So our result qualitatively improves the state-of-the-art separation because we show a quantum versus classical separation for a weaker quantum model, namely quantum simultaneous with entanglement, where Charlie simply does a swap test. So in this result, our second main theorem subsumes the previous separations between quantum and classical communication complexity. So this is the significance of our second result. And now let me tell you about the proof ideas. The main technical tool is a level K inequality for SUN. So I'll describe this inequality in the next slide. This inequality was developed by Ellis, Kindler, Lifshitz, and Minzer. They were trying to understand the size of product-free sets in SUN. So they wanted to understand what is the largest subset of SUN that does not contain 3 matrices ABC such that AB equals C. In trying to answer this question, they developed this level K inequality, which is a powerful analytic tool, and they used it to show that any large subset of SUN cannot be product-free. So any subset of SUN of measure at least e to the minus n to the 1/3 must contain 3 matrices such that AB equals C. This is the context in which they develop level K inequalities over SUN. In general, level K inequalities have been established over various domains, most notably the Boolean hypercube, the unit sphere, the Gaussian distribution, and so on. And these inequalities have several applications, most notably to the field of quantum versus classical separations in communication complexity. In particular, 2 of the results I mentioned before use the level K inequality on -1 to the n. One of these uses level K inequalities on the unit sphere, and our result uses level K inequalities on SUN. So here is the level K inequality on SUN. Loosely speaking, it says that a large set cannot have a large degree K component. To formalize the notion of degree K component over SUN, you can do it as follows. So let's look at all functions on unitary matrices. So functions that take in unitary matrices and output real numbers. Some of these functions can be expressed as low degree polynomials in the entries of these matrices, U and U dagger. We call these functions low degree polynomials. So L at most K consists of polynomials of degree at most K. If you subtract polynomials of degree K minus 1, you're left with polynomials of pure degree K. And this is what I mean by level K. And here is the level K inequality. It says that if you have a subset of SUN whose measure under the Haar distribution is alpha, if you take the indicator function of A, then the level K component of this indicator function has a small L2 norm. So here indicator of A equals K is the projection of the indicator function onto the pure degree K part. And this inequality says that the L2 norm square of this is small. I'm not going to have time to give some intuition on this inequality, but for those of you who have seen the level k inequality over the Boolean hypercube, let me just contrast these two inequalities. So over the Boolean hypercube, you have the following inequality. Given any subset of -1, 1 to the n of measure alpha, the level k component has L2 square at most. So it's very similar to the level k inequality over -1, 1 to the n, but this one works over SUN. And this is a very powerful inequality, and this is the main inequality we use to derive our lower bound. So in the next few slides, let me give you a very quick idea of how we use this inequality. So first, the main place where we use this inequality is in the lower bound. So to show that the ABCD problem has no classical randomized protocol of small cost, we first reduce the problem to a problem about rectangles. This is a very standard argument in communication complexity. If you look at the matrix where the rows are indexed by Alice's input and the columns by Bob's inputs, a communication protocol partitions this matrix into a few components. A protocol of cost C partitions this space into 2 to the C rectangles, and within each rectangle, the output of the protocol is constant. This is a very standard argument in communication complexity. And to prove the lower bound, we show that any rectangle that is not too small cannot distinguish a random yes instance of the problem from a random no instance of the problem. So this is our main technical lemma. More formally, we have the following result. Let P and Q be the indicator functions of Alice's and Bob's sides of the rectangle. These are just subsets of SUN times SUN. And we assume that these rectangles are not too small. So these P and Q have measured at least alpha and beta under the Haar random distribution. Then these two quantities are close. So what are these two quantities? On the left-hand side, you have the probability that a random yes instance is in this rectangle. And on the right-hand side, you have the probability that a random no instance is in this rectangle. And we argue that these two quantities are very close. This is our main technical lemma. And the way we prove this is by doing Fourier analysis and trying to decompose these indicator functions and then applying the level k inequality over SUN. So this is the big picture of our proof. Let me conclude by mentioning an open problem, which is the following. Is there an oracle separation between DQC1 and BPP? In other words, in query complexity, can you prove an exponential separation between the one clean qubit model and the classical query model? Typically, separations in communication complexity are harder to establish than in query complexity, but in this case, we believe this is an independently interesting problem that is of incomparable difficulty. So this brings me to the end of my talk. I'm happy to take questions now.
Okay, we again have a time for one or two quick questions.
Do you know if the communication complexity setting, there will be difference if you have the QC1 and the QC2 or K, let's say?
That's a good question. I think you can simulate a certain number of qubits using just one clean qubit. Although I think the scaling is different. In communication complexity, it is more like log n as opposed to log n. But I'm not sure, but I think this is it.
So for the oracle separation on this last slide here, is it a classical or quantum oracle separation?
Yeah, so ideally we want it to be a classical oracle because how would the classical algorithm access a quantum oracle? So
Right.
Yeah.
Okay, I see.
Okay, then let's thank Uma for this great talk again. Okay, so the next speaker is François Gall. So the stage is yours.
Okay, thank you. So I will talk about distributed quantum computing. So I will start with a brief description of classical distributed computing. So we consider a network represented by a graph with n nodes. So each node represents a processor and each edge represents a communication channel. For technical reason, we assume that all nodes have IDs, distinct IDs. Sorry. And each node initially knows nothing about the topology of the graph. And we have communication, but communication is synchronous. It means that communication occurs round by round, and at each round, nodes can send one message to their neighbors. So let's see an example here. At round 1, you have all the nodes exchanging messages. Then you have local computation, then another round of communications and local computation, and so on. And we are mainly interested in the number of rounds needed to reach a conclusion. Okay, let's see a concrete example. Computing distances. Assume that you want to compute the distance between node 1 and node 6. So the answer is 2, because there are 2 hops. The distance is 2 here. So how do we do this? So node 1 first send a message to its neighbors. And then all the nodes will receive a message, know that they are distance 1 from this node 1. And then all the nodes, the second round, all the nodes tell the new knowledge to their neighbors. And at the end of round 2, all the nodes that receive for the first time a message know that they are distance 2 from node 1, so they can update the distance and set distance equal to. Okay, you see for this problem, you can solve it in 2 rounds. So now I describe briefly the model, but there is a very important thing, which is the size of the message here. And there are 2 different submodels. In the first one, we assume that its message is very small, only 1 bit. In the second model, we assume that there is no restriction. We have no restriction on the size of the message. It can be very, very large. And so the second model, the local model, may look a little bit artificial, but actually it's even more well studied than this one, because it has a lot of motivation. Many practical situations, communication is very fast and cheap. And what's really bottleneck in the computation is the number of rounds needed to compute or to solve a problem. So now the quantum version, I will give more details later, but in a few words, it's exactly the same, but now we can send quantum message. So typically we assume that we don't have any prior entry. So each edge is now a quantum channel and you can send quantum message. And again, there are 2 submodels, the congest model where you can send only 1 qubit per message, and the local model where there is no restriction on the size of the quantum message. And the congest model is very related to communication complexity because since each message is very short, the number of rounds relates to the overall communication complexity. And indeed, there are several known examples of quantum advantage, typically polynomial speedups obtained recently in the quantum congest model. For the local model, on the other hand, there are very few results. And this talk focuses on this local model. Okay, so now I will give more details about this local model. So typically, we consider a bounded degree graph. That is a graph where each node has degree upper bounded by a constant, and the node do not receive any input except the IDs. And we typically want to solve a problem related to the whole graph. So for example, computing a coloring of the graph. Okay, and the classical deterministic algorithm will work as follows. So initially, you don't know anything. The node knows nothing about the topology, except, of course, the ID. And after 1 round, they learn the labels of their neighbors. After 2 runs, they learn the neighbors of the neighbors. And after 3 runs, the neighbors of the neighbors and the neighbors, and so on. Okay, and you can actually show easily that this is the optimal strategy for classical deterministic algorithm. Okay, without loss of generality, you can always assume that R-round classical deterministic algorithm learns first its R-op neighborhood and then compute their output based on the knowledge they get. Okay. So this means that for classical deterministic algorithm, the number of rounds needed is equal to how far do you need to see in order to solve a problem. So we have a very nice characterization here. And indeed, this can be used to prove tight bounds on the classical complexity of many problems. And a very basic and fundamental problem in the local model is three coloring rings. Okay, so you have a ring here, and here is a three coloring. So three coloring means that we need to color each node by one color. There is only three colors available. And the condition is that neighbors should have distinct colors. For example, you have green here, and indeed the two neighbors here have distinct colors. And it's known that in the deterministic local model, the classical local model, a three coloring can be computed in log star n rounds. So what is log star? Log star is defined as this, but it's not, the definition is not really important. The very important thing is that it's a very slowly growing function, extremely slowly growing function, much slower than log, log, and so on. So for example, the log star of this big number is 5. It's not constant, but very close to constant, right? Okay. And you may wonder what I'm talking about three coloring and not two coloring. Indeed, if n is even, a ring will have a two coloring. But the point is that computing a two coloring of a ring is very difficult. It requires a linear number of rounds. So it's not a very interesting problem in distributed computing. The three coloring version is much more interesting. Okay, so now the quantum local model. Okay, so again, the difference is that now we can send one quantum message between adjacent nodes per round, and again, the length of the message is unbounded. So if you consider this simple network, a path of 4 nodes, at each round, the nodes can exchange messages. We can rewrite or interpret a quantum distributed algorithm using a quantum circuit, and sometimes it's useful. So for example, if you have, So if you have a 0 round of communication, nothing happens. So you simply do local computation and measure. If you have 1 round, then you have communication. So you have 1 additional layer. So this box means exchange of the register, quantum register. And then we measure. So if you have 2 rounds, we have 2 additional layers, and 3 rounds, 2 again additional layers. And so okay, so we will use this interpretation in a few minutes. And of course, the main question in quantum distributed computing is to understand whether we can get an advantage, a quantum advantage. And in the local model, we know that this is the case. There are 2 prior works. We know that there exists a computational problem that can be solved in constant round in the quantum setting, but requires a linear number of rounds classically. So this results improves the previous 1 versus 2. Now it's a constant versus n. It's a very huge gap. But there are 2. So first, what problem is it? It's simply sampling from the outcome of a quantum circuit that measures graph state in a random basis. Okay? So in a constant number of rounds, we can construct the graph state corresponding to the whole network, and then locally the node can measure the graph state in a random basis. And we can show that simulating sampling from the same distribution requires a linear number of rounds in the classical setting. So there are 2 weaknesses. The first thing is that this computational task is not really useful. And the second one is that the solutions are not efficiently checkable. Checking if we have a valid sample requires actually a linear number of rounds. And you see that the situation is very similar to quantum supremacy results. There are many papers on quantum supremacy with circuit that typically show that a weak quantum circuit can do things that a strong classical circuit cannot do, but also we have the same weakness. Typically it's for very artificial problems, sampling problems, and it's very hard to verify the supremacy. Okay, So the really interesting question are the following two questions. So can we prove a quantum distributed advantage for a problem that someone actually cares about? Or can we prove a quantum advantage for a problem that is efficiently checkable? And this is open, widely open. Okay, let's come back to this recoloring. So it happens that this problem is efficiently checkable. It's very easy to check if a candidate is a three coloring because each node only needs to compare its color with the colors of the two neighbors. This can be done in one round. Okay? And classically, we know how to do it in log star n rounds. So the fundamental question, one of the most fundamental questions in the field is whether you can do better. So for example, whether you can achieve constant round in the quantum setting. And this question is open. It has been asked in the very early papers on quantum distributed computing. Okay. So actually, almost all the problems studied in the literature on the local model have the same property as three coloring. They are locally checkable, which means that you can check if the solution is a valid solution in a constant number of rounds. So we can refine a little bit the question and ask whether we can prove a distributed quantum advantage for a problem that is locally checkable. And this is the question we are considering in this work. And so I've talked with many people working on classical and quantum distributed computation. It seems that the natural conjecture is that the answer is negative. So if you require the problem to be locally checkable, then it seems that that doesn't there is no quantum advantage, at least in the local mode. And this work try to make progress on this conjecture. Okay, and we do this by introducing the concept of causality. Okay, so you all know that quantum mechanics satisfy causality. So what does it mean for quantum distributed algorithm? For example, for this two-round algorithm, if you look at the output of this node, the bottom node, so the output only depends on the input within the like cone. This means of the input of these three nodes. So more generally, for any quantum distributed algorithm, you can have some relation between the input and the output using causality. And we can go further and define the concept of non-signaling algorithm. Okay, the key idea is to define a model so that it can do anything except violating causality. And this has been done in prior work. And here is the definition. So for any set of nodes X, so the yellow nodes here, if you consider the blue nodes here, which are the node at distance at least R from the orange node, so any change in the blue node does not influence the output distribution of the orange nodes. Okay, so any probability distribution satisfies that property is called the R-op non-signaling distribution. And you see that we are talking here not about algorithm, but about distribution. Okay, so non-signaling distribution, probability distribution. Okay, so we have three models: classical, quantum, and non-signaling. We don't understand well quantum distributed algorithm. We want to understand this better, and we would like to try to prove or disprove this conjecture. But the point is that we can't understand fairly well the classical algorithm because we have a nice characterization. And we may be able to understand well non-signaling algorithm also because it's essentially related to probability theory, to classical probability theory. So a natural approach to solve this conjecture will be to show that for any locally checkable problem, non-signaling algorithms are not more powerful than classical algorithms. This will prove that classical is equal to non-signaling. And since quantum is between, this will prove that everything collapses. And this will prove the conjecture. Okay. And this has been proved, actually. This thing has been proved for two coloring in rings. We know that non-signaling is not more powerful than classical for two coloring in rings. We also know, this was yesterday's talk, that the same thing for graph coloring in arbitrary bipartite graphs. But what we would like to know in order to prove the conjecture is to show the same for any locally checkable problem. And in this result, in this paper, our main result states that actually this natural approach doesn't seem to work because there exist many classes of locally checkable problems for which non-signaling algorithms are much more powerful than classical algorithms. Okay? Of course, we have a positive interpretation of this. This means that actually there might be a quantum advantage at the end. So it's even more exciting a perspective. Okay, so now I will give a slightly more precise description of the main result. So actually in the paper, we consider many models. So in the introduction of the paper, we have this figure with a lot of models, both classical and quantum, and we prove a lot of relation between all these models. But in this talk, I focus on the model related to quantum, which is a quantum model, the classical model, and the non-signaling model. And our main result says that any locally checkable problem that can be solved in small or log n rounds in a deterministic local model. This means here, any locally checkable problem that can be solved with this complexity in this model. Then it can be solved in constant complexity in the non-signaling model. Okay? And we have one example, which is a three coloring in rings. Classically, I say it's a log star. Log star is a big O of log n. So you get constant complexity here from the theorem. But for three coloring, it was already known. So there was a few papers by mathematicians showing this. So it's not new for three coloring rings. But our theorem says that it is true for any locally checkable problem with this complexity. Okay, and this means that the natural approach to solve the conjecture does not work for a very large class of problems, all the problems with this complexity in the deterministic setting. And as I said, this positive interpretation is that there might be actually a quantum advantage. And the second result is about trees. So the first result was about network of arbitrary topology. The second result is about network with topology corresponding to a tree. So we show that in tree, any locally checkable problem that can be solved in small or log n runs the non-signaling model. So here, non-signaling model, this complexity can be solved classically, even deterministically with this complexity, much smaller complexity. So what does it mean? This means that in trees, there is no locally checkable problem with locality in this region in the quantum local model. Why? Because if there is complexity here, this means that the complexity is smaller than log n, and you can use the theorem to get complexity here, much smaller complexity. So we know with the theorem have a much better understanding of the complexity of problems in the quantum local model over tree, at least. Over trees, there is nothing in this region. It can be here, there is something here, but nothing in the intermediate region. Okay, so in the last few minutes, I will try to give an overview of the proof of the main theorem. Again, the main theorem says that if you can do something in smaller log n in the deterministic setting, you can do it in constant complexity in the non-signaling model. And we use two tools. The first tool is from the prior works I mentioned earlier. It says that there is a constant round non-signaling strategy for three coloring a ring. And the second tool says that there is a reduction from prior work from the blue thing here. So any locally checkable problem that can be solved in log and round in the deterministic local model to the problem of computing a D+1 coloring of the graph, where D is a maximum degree of the graph. And based on these two tools, we prove the theorem by using the following 4 steps. First, we extend the result of tool 1 from a ring to a coloring what we call a pseudo-forest. A pseudo-forest is a generalization of a tree. Then we show that any bounded degree graph can be as a nice decomposition into pseudo-forest. And then we combine 1 and 2 to obtain a D+1 coloring for any graph of maximum degree D. And finally, we use the second tool in order to obtain the claim of the theorem. And all these things are a little bit technical, but the main insight here is really this tool 1. So I will spend the last 2 minutes describing this very, very nice non-signaling strategy for 3-coloring a ring. Okay, so we consider the following probabilistic process. We have a ring. We first put at a uniformly random position a uniformly random color. Say, for example, here. Then I put a different uniform color at a different position. So say, for example, here. I put blue here. And then I repeat the following. I pick a uniformly random node between consecutive colored nodes. So for example, let's say this one. And I insert a color different from the 2 colors of the neighbors here. So it will be a green here. And you continue. Say I take this one and I put it in orange. Then say I will take this one and it will be blue. And you continue like that. Okay, and if you continue like that, what you will get is a valid 3-coloring of the graph. It's obvious to see. So what this probabilistic process is producing is a probability distribution over valid 3 colorings of the ring. And now the surprise is this theorem that says that the restriction to any sets of vertices at distance greater than 2 are independent of each other. For example, if you take the set of this set and this set, the distance is at least 2, it's greater than 2. So these marginal distribution are independent. We can show this. It's fairly surprising. And from this property, we can conclude that we have a one-hop in our definition to become the 2 here become a one-hop non-signaling distribution. So you get a constant round non-signaling strategy for 3-coloring a ring. Okay, so this is the main technical result used in our proof. So I will conclude now. So we have shown several relations between the classical quantum non-signaling local models and also many other things that I didn't mention in the talk. And the main message, at least for the quantum community, is that for a large class of problems, it's not possible to exclude quantum advantage by using non-signaling arguments because non-signaling strategies are extremely poor. But of course, again, its positive interpretation is that there might be a quantum advantage. So the main open problem is to try to find a problem exhibiting a quantum advantage. The second one is maybe to exclude quantum advantage not for all problems, but for one specific problem. For example, we can try to focus on 3-coloring in rings. And the last one is to understand whether shared entanglement helps for any locally checkable problem. This is an open question. Okay, thank you.
We again have time for 1 or 2 short questions.
So in general, what is the complexity for locally checkable problems? Is it always like log star n, or is it larger, smaller?
It really depends on the topology. So classically, if you consider a ring the situation is very simple. We have only three classes, classically: constant, log star, and linear. Okay? And depending on the topology, you can have more classes. But there is typically only a constant or a small number of complexity classes. And most practical problems have complexity very small. Log n or log star n, we are really very, very low in the complexity for many practical problems.
Okay, can I ask another question? So for, in the end, you show the, I don't remember the name, the, the last algorithm you show, like, I understand the fact that you have a light cone in the conclusion, but the algorithm itself doesn't seem to have any light cone property there. Like, you do things at a global level of the graph itself. So
yes.
I'm
yes.
confused.
Yes, yes. So it's not an algorithm, actually. It's a strategy. That's why I use strategy and the distribution. So the point is that what we call non-signaling distribution, non-signaling strategy, doesn't mean that we have an efficient way of generating the thing. Okay, it simply says there is a probability distribution, that probability distribution, and it satisfies this property, which means that you have a non-signaling property when you look at the marginal of this probability distribution. It does not say anything about how to generate it concretely from the input. But we know that the complexity here is an upper bound on any quantum distributed algorithm.
Okay, I see. So you just need the existence of something.
Exactly, exactly.
Thank you for the talk. So, I guess on that note, I was curious, what are a couple other examples of problems in this model? Like you mentioned colorings on rings, but I'm wondering what other graph problems are, studied in this area.
Yes, so as I just mentioned, so if you consider rings, again, there is only three classes. So a log star will be all the problem equivalent to 3 coloring. We will have constant, which are all the trivial problems. And we will have n linear complexity, which are all the problem equivalent to 2 coloring of a ring. So over a ring, really, we have only 3 classes of problems. And when you get to more complex topology, you can get more, a few more problems. But typically, we have only a constant, as I just said, a constant of small number of classes, and each class has one representative problem, and everything becomes you can reduce everything to this few numbers of problems.
Very interesting. And do those classes, do those representative problems tend to be colorings?
Often coloring, yes.
Are there any counterexamples?
Yes. So you have problems like computing a good orientation of the graph, sinkless orientation of the graph, and things like that. Yes. So there are a few other problems, but coloring is by far the most important problem in all this theory of locally checkable problems.
It's a very interesting model. Thank you.
So let's postpone the discussion for later, and let's thank François again for this really nice talk.